So we had started section 8.4 last week, so let's review very, very quickly here. This is using chemical equations to figure out what mass of something will react or produce what mass of something else. And our map, our path here is mass, which is generally grams, and so we'll say grams to moles to moles to grams. And the other night I was actually reading Dora the Explorer to the irrational 4-year-old. I don't know why the little boy likes to listen to Dora stories, but whatever. But I was just struck again by, who do we ask for help when we don't know which way to go? The map. So in this chapter, this is your map. Okay? Grams to moles to moles to grams. It's the same. Okay? So this is your map. It's dumb, but you might remember it. We did this problem. We're going to do another one. So we're going to do this one. So this is saying what mass of octane would be needed to generate 42.3 grams of oxygen. So on your paper, you should write the balanced chemical equation. You can leave out the state symbols because they don't really matter here. Write that on your paper, and then use that equation to help you organize the numbers. And I don't really have enough room in here to do it, but I'll squish it in there anyway. So what mass of octane? So that's our question, right? Where is the octane? Well, hopefully, at least by process of elimination, you can figure out that C8H18 is mass. And so question mark grams. That's what we're trying to find. And the information they give us is 42.3 grams of water. So over here under water, I can't remember that one, 42.3. My short-term memory is gone. 42.3 grams. So we have 42.3 grams of water. We want to know how many grams of octane we can have. Mass to mass. So what's the path? What's the map? Grams to moles to moles to grams. Okay, so that's our pattern. So we're going to go grams to moles to grams. So we're going to start out here with 42.3 grams of, and you need to write the formula in there. This map has 3 arrows, and so we're going to have 3 conversion factors. 1, see, make sure I leave enough room. 2, 3. This is dimensional analysis, and this chapter is the most important reason that you need to understand dimensional analysis, because if you get dimensional analysis, this is not a big deal. If you don't get dimensional analysis, you're going to struggle here. Grams to moles to moles to grams. So grams of water to moles of water. And then to moles of the thing we're looking for. Moles of octane, C8H18. To grams of octane. The map tells us what to do. Grams of the first thing to moles of the first thing, to moles of the second thing, to grams of the second thing. And I had a student ask me yesterday, very good question, why do we have to do this long process? Isn't there a shortcut? Why can't we just go grams to grams? Well, we could figure out a conversion factor that would relate grams of water to grams of octane. But it would only work for this one particular reaction. And so we would end up needing a zillion, literally, conversion factors to do these sorts of problems. It's not worth figuring out all those conversion factors. This way, grams to moles to moles to grams, the conversion factors we need come from the balanced chemical equation and from molar masses, which we calculate quickly from looking at the periodic table and the chemical formulas. The reason is that particles interact based on numbers of particles, not on their masses. To make water, you need 2 hydrogen atoms and 1 oxygen atom. Okay? It's not, 2 grams to 8 grams or whatever. It's based on particles. And the balanced chemical equation gives us particles. Okay? It tells us the relationship in particles. Well, mole is just a larger counting number, like dozen. Dozen means 12. Mole means a really, really big number. Okay, so mole relates the numbers of particles. But that's not very useful to us, practically, and so we need masses. So we have to convert our mass to moles, so then we can see the relationship in number of particles, and then we convert to mass again so that we could weigh it. So that's why. Maybe nobody wanted to know, but now you've got an explanation. Okay, so we put in the numerator, and to put the denominator in, we take the previous term and we stick it in the bottom. Because we don't want to end up with grams. Okay, so we've recreated. So in the bottom here, we go with grams of water. And, oh, yeah, I got tripped up when I was going to try to cancel those out. We want to cancel those out. And then over here, we want moles of H2O, so that those cancel out. And over here, we want moles of C8H18. Now, if you have a question, if you don't understand something, please ask me, okay? Or if you're just like, I'm so lost I can't even ask a question, just say that, okay? And I'll explain and we'll work on it. Because this stuff isn't going to go away. It's not going to get better when you go home and look at it by yourself. It will get worse, much, much worse, okay? So we've got our units in there. I'm going to cancel these guys. The units are our friends. They tell us what to do, okay? Now we need to put in some numbers that give us the relationships between those numbers, those units. And the easiest one is in the middle, moles to moles, because that's in the equation above. So in front of C8H18 is what number? The number 2. So then, down here in front of C8H18, I put the number 2. And in front of H2O is the number 18. That's a really big number. It's okay. It's okay. There are some big numbers in chemistry. 18. Okay, because when we look at this equation, we can kind of imagine that, it's 18 molecules of water, or it's 18 moles of water. It could be either one. Or it could be 18 dozen water molecules. That's just not a real useful unit to chemists. Although we still, buy our bagels by the dozen. But so over here, mole. So it's 2 moles of octane gives 18 moles of water, and that's where that conversion factor comes from. The moles and grams, the grams and moles, that's the molar mass. We learned how to do that. I think that was chapter 7. And so we have to do that. So we look at the formula H2O. There are 2 hydrogens, and 1 oxygen. So that comes out to 18.016 grams of water equals 1 mole of water. So in my equation here, I've got 1 mole of H2O is equal to 18.016 grams of water. Now technically that just has the 4 significant figures, but it's good to carry extras. C8H18, we've got 8 times the mass of carbon and 18 times the mass of hydrogen. Yeah, I always read my calculator up. It's always good to do it yourself on the calculator. Like when you're in lab, don't rely on your partner's calculation because sometimes they do it wrong. Do it yourself. 114.224. 114.224 grams C8H18, that's not an 18, that's an 8, equals 1 mole. Okay, so that goes up here. And I didn't leave enough room because I just don't have enough room. And again, that has technically 4 significant figures. So everybody following me? I don't believe you, but that's okay. 42, so we're going to go left to right, multiply by things on the top, divide by things on the bottom, so we don't leave anybody out. So 42.3 times 1 if you want to, divide by 18.016 times 2. Divide by 18 times 114.224, divide by 1, equals. Now how many significant figures should this answer have? It should have 3, because our starting number was 3. And generally in these calculations, it's the starting number that limits your answer. I don't think I have room to write it down there. So I'm going to say equals and draw an arrow. So the calculator says 29.798, blah, blah, blah. So we're going to round that to 29.8. So 29.8 grams of C8H18. Any questions? This is like a bread and butter calculation for a chemist. We do lots and lots and lots of these. No questions. Here's another example. Some of these have little stories behind them, which you may or may not find interesting. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to this reaction. Do you really need any of that? No, you don't. You need the equation and you need the question. How much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? You need the balanced chemical equation and you need the question down there. Okay, so how much HCl in grams? So under HCl, I'm going to write a question mark and gram. That's what I'm trying to find. And then it's asking, it says 5.50 grams of magnesium hydroxide. So under that, 5.50 grams of that. So I've got grams to start with, and I'm finding grams, so the map is grams to moles to moles to grams. And you know you've studied enough when you wake up in the middle of the night suddenly muttering grams to moles to moles to grams, and having nightmares about it. Then you know that you're maybe getting there. So 5, well, we should just write that out. Grams to moles to grams. So 5.50 grams of magnesium hydroxide. 3 conversion factors. Times. On the top, grams to moles to grams. So grams of magnesium hydroxide to moles of magnesium hydroxide. And yeah, you need to write the formula in there. To moles of HCl to grams of HCl. That's our map, our path. And then in the denominator on the bottom, we put the previous term. And try to leave room for numbers, but sometimes it's just really not possible. I had to do this on the board in Reedley yesterday because I got there and I realized I left my iPad at home. Oops. The nice thing about the board is it's really wide and there's lots of space. So moles of HCl cancel moles of HCl. Moles of magnesium hydroxide cancel moles of magnesium hydroxide, and grams cancel grams. You can fill the numbers in any order that you want. I think it's always nice to start with the easy one. The easy one is in the middle. What number is in front of HCl in that equation? It's a 2. So we put the 2 in front of HCl. What number is in front of magnesium hydroxide?
1.
It's an implied 1. Chemists don't seem to like the number 1. But really, the number 1 is a really skinny number, and so maybe this is just a really, maybe an anorexic number 1. And it's so skinny you can't even see it. So we got those in there. Then we need molar masses for these other guys. So magnesium, 24.31. And this is where it's really important to understand what these formulas are saying. The 2 on the outside of the parentheses multiplies everything inside the parentheses. So there's 2 oxygens and 2 hydrogens. So 24.31 plus 2 times plus 2 times, and I get 58.326. Grams. Now this part, do you have to write this part out? Grams of this equals moles of that? Not necessarily, but I just want to be clear so that if you come back and refer to this, you'll know, where did you get that number? Come on, move. Thank you. Talking to the iPad. Because I'm crazy that way. It's amazing I'm as sane as I am. So 58.36. Yeah, I'm recording. Well, I started it up again. Good grief. That's okay. That was Wyndham blowing in his nose again. He's got a really bad cold, and we're thankful that he chooses to come anyway. And your germs. Okay, so then HCl 1.008 plus 35.45. So that's what? 36.458. Grams of HCl is equal to 1 mole of HCl. So that comes over here, 36.458. Any questions? What we're doing is we're putting together several things that we've learned in the past. We're taking the concept of dimensional analysis and converting units, and the idea of molar mass and mole ratios from balanced chemical equations, and we're just putting them all together now. 5.50 times 1 divided by 58.326 times 2 divided by 1 times 36.458 divided by 1. So, some people really want there to be a number 1 there, and that's fine. But, if you multiply by 1 or divide by 1, it doesn't change the number. So if you don't want to write those ones, you don't have to. So I'm going to write the answer up here. How many sig figs should our answer have? 3. So this number is going to round to 6.88. Anybody else come up with that number? Yeah, okay, good.
A number's a little off, because like 1.01.
Yeah, it could end up being a tiny bit different in the last digit, depending on how you round it. So this is equal to that. Some periodic tables round everything to 2 decimal places, and so then things like hydrogen only have 3 significant figures, and so, it's a very minor difference, but, people who are detail-oriented, then they come up and they're like, why is mine a little different? It's okay. So if you was yours 7 or 9?
Mine would tend to leave it a rule, mine was
9. So if you came up with 6.89 on an exam, and 6.88 was one of the choices, and also none of the above, 6.88 and 6.989 differ only in the uncertain digit. Differences in the uncertain digit are okay, so don't choose none of the above. That's about the only time that's really going to mess you up. Any questions? Another example. Oh, joy. One component of acid rain is sulfuric acid, which forms when SO2, a pollutant, reacts with oxygen and rainwater according to the following reaction. Assuming that there is more than enough oxygen and water, how much sulfuric acid in kilograms forms from 2.6 times 10 to the third kilograms of SO2? Okay, so that whole first part is all very nice and everything, but we don't really need it, do we? So I'm going to try something. Okay, so I just blacked out that part at the top so that I could have a little more space. So in our equation here, it's saying how much in kilograms of sulfuric acid. So under here I'm writing question mark. So I think I'm going to go to yellow. I don't know why, just because. Question mark kilograms. And that's what they're asking us. And then they're telling us that we have 2.6 times 10 to the third kilograms of that. Now, you might find the whole kilogram thing disconcerting. But what do? We're doing grams to moles to moles to grams, and now it's kilograms. Ah. Bless you. Everybody's ill. Okay, so let's think about this. So our map is grams to moles to moles to grams. Okay, so if we've got kilograms, then we could start with kilograms and convert to grams, right? And then at the end we can convert from grams back to kilograms.
Figure it out. Could we get 3 grams and convert it and multiply it by 1,000?
Well, there's different ways we can think about this, and so I'm just going to think through a couple of these ways with you. So when we convert from kilograms to grams, we end up multiplying by 10 to the third grams over 1 kilogram, because kilo means 10 to the third. And over here, going from grams to kilograms, we end up with kilogram over 10 to the third grams. If you have those terms at the beginning and the end of your equation, they essentially cancel each other out, don't they? So, do we really need to do them? No, we don't. So there's another way we could think about this. So I'll go up and use the space I created at the top. Grams to moles to moles to grams. Well, we're starting with kilograms. That's a bad K. And that's not even close. Okay. And we want to end up with kilograms. Do we know the relationship between moles and kilograms? The molar mass gives us moles to grams. Could we do kilomoles to kilograms? Yeah. Because, if a gram of something, well, let's just carbon, 12 grams is 1 mole. Then 12 kilograms will be 12 kilomoles, right? Let's actually write that out. So 12.01 grams, I'll leave some space, grams of carbon equals 1 mole of carbon, right? That's a molar mass. of an element. So what, if I multiply this side by kilo and that side by kilo, is it still equal? Yeah. If you do the same thing to both sides, it's still equal. So you can do what I did on the bottom and throw an extra step in front and behind. I really don't want to do that, mostly because it's not going to fit on here, and that's going to be awkward, and I don't like that. So I'm going to do this on the top. I'm just going to throw kilo in front of everything, and then I think we'll be just fine. So I need to erase that. Okay, so I'm going to start with kilograms. So 2.6 times 10 to the third kilograms of SO2. And I'm going to have 3 conversion factors. And I'm going to follow my map. This time it's kilograms to kilomoles to kilomoles to kilograms. It just doesn't have the same ring to it, does it? Kilomoles of SO2 to kilomoles of H2SO4 to, this is, oh, such a mess. That's not right. Kilograms of H2SO4. We okay with that? Basically, I scaled up the recipe. It's like, my boys play football, and then we have to make dinner for the whole football team, So now you're cooking for like 40 people. So you take your recipe that serves 4, and you multiply by 10. And then you double it just because they eat so much. Anyway, but you just multiply everything by 10, and it all comes out right. So here we're just multiplying all of these things by 1,000, and it'll be okay. So we put the units in, and then we put the units in on the bottom, kilograms of SO2 and kilomoles of SO2.
If we just took out the kilo, it would still
Work.
it would still come to the same ratio.
And kilomoles of H2SO4. So if we were doing a regular thing where we're just doing grams to moles to moles to grams, all we'd have to do is we could erase all of those Ks, and we'd end up with the same thing. The problem is that the question is giving us kilograms and asking us for kilograms. This is not the only way to get around it, but we should understand what these metric prefixes mean well enough that we can deal with them even when they get thrown into another problem. So the moles are the easy one. In front of SO2, we see the number 2. And in front of H2SO4, we also see the number 2. 2 molecules of SO2 would make 2 molecules of H2SO4. 2 moles would make 2 moles. 2 kilomoles will make 2 kilomoles. 2 teramoles would make 2 teramoles. The terabyte drives and stuff that they have for computers, tera is a metric prefix. It means really, really big. I think it's
15 zeros or 12 zeros?
I think it's like 15. Giga is 12, I think, and tera is probably 15. Generally go by 3s.
Above tera.
There are things above tera, I just don't know what. Yeah, they've got all these weird names, and I just remember the ones that I actually run into. So then we need some molar masses in here. SO2, 32.07 plus 2 times 16. 32.07. Turn the calculator on first, that always helps. 64.07. And see, normally we would say grams of SO2 equals 1 mole of SO2. And that's true. We can multiply each side by 1,000 and stick kilo in there, and it's still true. So we're going to stick in here 64.07. But I didn't cancel my units. So these are canceling, and those are canceling, and those are canceling. And then we need H2SO4, 2 times hydrogen, and 1 sulfur, and 4 oxygens. $58.086. That's not right.
This is 4 times 16.
It's got to be bigger than SO2. So start over again. 4 times 16 plus 32.07. I'm doing it backwards, I'm sorry. 2 times 1.008 equals, that's better, 98.086. Okay, and that's kilograms of H2SO4 equals 1 kilomole of H2SO4. So that squeezes impossibly into this little space, 98.086. Nice. Not. Okay, now if we can read my handwriting. Don't forget how to use scientific notation. 2.3 EE3 times 1 divided by 64.07.
2.6.
Thank you. 2.6. I'm looking at 2.6 and I'm saying 2.3. 2.6 EE3 divided by 64.07 times 2 divided by 2 times 98.086 equals. And I did something. What did I do? I screwed it up again. I've been working on new ways to screw things up. I'm being really successful at it.
It's just to make sure you still can.
Yeah, just practicing, because I thought I was getting out of practice at screwing things up. That's better. I came up with 1.37 or something. This has to be a big number. Okay, I'm going to change colors so that we can see what I'm doing, because I'm out of space. So that's not even a good arrow. So this comes down here. So this is what my calculator is showing me. 3980.39 blah, blah, blah. How many significant figures should this number have?
4?
2.
Where's that letter?
The original number that we were given had 2.
Oh,
The 2.6 only has 2 significant figures. The molar masses both had 4. Those mole ratios are exact numbers. They're counting numbers, because 2 molecules makes exactly 2 molecules. Okay? So the mole ratio never limits the number of significant figures. So 2 significant figures would be right there. This is where you can get into dangerous territory. Okay? So if you are rounding off numbers, digits to the left of the decimal place, you better put it in scientific notation first. So I'm going to put this into scientific notation, 3.98039. There were other digits there, but that's okay. Times 10 to the third. Now I'm going to round to 2 decimal places, 3.98. The 8 makes the 9 round up to 10, which rounds the 3 up to a 4. Like, can we make this more complicated? Yeah, we could, actually. So we need to make it 4.0. The temptation is to just write 4, but now you've gone off to 1 significant figure. So the answer is 4.0 times 10 to the third kilograms of sulfuric acid. And especially when your work gets all messy like that, a box around your answer is awesome. It's like, all that scribbling, there's our answer right there. Any questions about that one?
On the test, will you give us a lot of space to work out these problems?
On the test, you can write on the paper, and I will also provide you with blank scratch paper if you ask for it. So, yeah, there's no limitation on space. I have to figure out how to do this better.